All right, class. So these couple examples should help you out with this week's homework for Module 3, which is related to a series and parallel AC circuits. And so for the first example, we're going to go through two examples. The first one is going to be a series network, and then the next one will be a parallel network. So for the first one, it says calculate the total impedance, total current, voltage across each element using the voltage divider rule. And so you want to make sure you are using, whenever you're showing your work, you are using the voltage divider rule. You can use Ohm's law to do this example, but this particular one, and in your homework, it'll specify which method it wants you to use. And if it says using the voltage divider rule, that's what I'm going to be looking for, that you use the voltage divider rule. So it says calculate the total impedance, total current, voltage across each element using the voltage divider rule and the power factor of the network below. All right, so first thing you want to do whenever you get a problem like this is to make sure all of your elements are converted to its respective reactance. So right here, the elements are given, the capacitor is given in farads, and the inductor is given in henries. So we want to convert these two elements, your inductor and your capacitors, to its respective reactance, like so. So your XC1, the formula for to convert a capacitor to its reactance is 1 over 2 pi FC. And remember that you have a negative J associated with the capacitive reactance. And so once we plug and chug our values in, we get negative J times 1 over 2 pi F, which is the frequency, 1.5 kilohertz, times the capacitance, which is 6 microfarads, which is given up here in your problem. And so once you calculate that all out, you get negative J 17.68 ohms. And you can convert this to its polar notation. So right now, this is just in rectangular. This is in rectangular notation. It may look a little different because it doesn't have a real component, because capacitive and inductive reactance are both imaginary. So this is just your imaginary component of your rectangular notation. But if you want to convert it to polar, all you do is just take that 17.68 and put it in front of a phase angle of negative 90. Okay. So capacitive reactance always has a phase angle of negative 90. All right. And so for our inductor, to find the inductive reactance, the formula is J 2 pi FL. And so we just plug and chug. So we get J 2 pi times your frequency, 1.5 kilohertz, times your inductor, which is 3.7 millihenries. And once you calculate that all out, you get J 34.87 ohms. And you want to go ahead and convert it to its polar notation, which is 34.487 with a phase angle of positive 90 degrees. Okay. And so now we have everything converted to its respective reactance. We don't have to do anything with the resistor. It's already in ohms. But these components right here, we want to get in ohms, which is its respective reactance. I mean, we've done that. So now you should be familiar with this. So in order to find the total impedance, we just add our elements together. So you got R1 plus XC1 plus XL1. And we'll just plug and chug. And you can just throw this into your calculator. I don't expect you to show your conversions, but let your calculator do the work and convert this guy from a rectangular notation to polar. Okay. And if you need some help with your calculator on how to do that, just let me know. All right, so now we have our total impedance. And so we can calculate our total current, which is your source voltage, which in this case is denoted as V1. See, V1, but that's just your source voltage divided by your total impedance. And so by plugging and chugging, you get 100 with a phase angle of 60 degrees divided by your total impedance, which is 52.87 with an angle of 18.97. And that equals 1.89 with an angle of 41.03 degrees. All right, so we found so far, we found our total impedance, we found our total current. So now let's find the voltage across each element. So in order to use the voltage divider rule, you need to know your total impedance, and you need to know the source voltage, which is V1. And so once you know those two components, then you can use your voltage divider rule to find the voltage across any one of the elements in your network by using that formula. All right. So the first one we're going to do is for finding voltage across R1. So we have VR1 equals V1 times R1 over your total impedance. And so by plugging your values in, you get 94.57 with an angle of 41.03. So make sure, depending on your calculator, you may have to put this guy in parentheses, depending on the settings of your calculator. If you're using the TI-30X Pro, I recommend you use this key right here that looks like this. It's like two boxes on top of each other. And so pretty much that lets the calculator know that whatever's in this top box right here, the top part of the fraction is the numerator, and whatever's in the bottom is the denominator. So what happens a lot if you use just the division sign, it's gonna put some value right here divided by some value right here. And sometimes this part, the angle gets left off if you're not careful. So if you're using this way, make sure you put it in parentheses, just like that. All right. All right. So, and then we just apply the same method to the rest of the elements. So XC1, trying to find the voltage across that one. We use the same formula. And once you plug it into your calculator, you'll get 33.44 with an angle of negative 48.97 volts. All right, and the same thing for your inductor. You get 65.95 with an angle of 131.03. Now, if you wanted to check your work, we know Kirchhoff voltage law is the sum of the voltages drops across each one of these elements should equal the source voltage. So therefore, if you add each one of these voltages, that one, And that one, you should get something relatively close to 100 at a phase angle of 60 degrees. So go ahead and give that a try and see if you get that answer. All right. All right. So the last thing we need to do was find the power factor. Now there's a couple different ways you can find the power factor. This is the first way I want you to learn how to do it. We're really the first couple ways I want you to learn how to do it. So power factor, the formula to find the power factor is the cosine of your theta V, which is your voltage, your phase angle of your voltage source, minus the phase angle of your total current. So we come up here, we find the phase angle of our voltage source, which is 60 degrees, and the phase angle of our total current, which is right here, right? 41.03. All right. All right. So once we calculate that all out, we get 0.95. A power factor of 0.95. And so at this point, we don't know whether or not if it's lagging or leading. We're going to figure that out later. But I wanted to show you this other method, which is you take the power factor is also equal to the cosine of your phase angle of your in total impedance. So let's look at phase angle and total impedance. You'll notice something very, very similar to what we just calculated. So the phase angle of your total impedance is a positive 18.97 ohms. I mean, 18.97 degrees. Excuse me. So you just plug it into your calculator, and you get the same thing: 0.95. Power factor equals 0.95. And so essentially that's the same thing. So let's say, for example, you were only given the total impedance. You were only given this total impedance. So basically, I mean, you really don't need to know any more information to determine the power factor. So you know the impedance. You can come down here to this equation right here, cosine of the phase angle of your impedance, and find the power factor. All right. Likewise, if you knew the phase angle of your voltage source and your total current, you can use this equation. All right. So now we need to figure out whether or not if these power factors are lagging or leading. And similar to what we did with our last homework, you want to take the phase angle of your current. So let me back up. So power factor is always with respect to, is always with reference to if the current is lagging or leading the voltage source. All right. So there's a couple different ways you can state that whether or not if determine the whether or not if a sine wave of current and voltage source is lagging, leading. You can say the voltage source is leading the current by certain degrees. You can say the current is lagging the voltage source by certain degrees. But whenever you're talking about power factor, it's always with reference of how much is the current leading or lagging the voltage source. Okay. And so that's what we're going to do in this class. We're going to focus on learning that way. So so you take your current, your phase angle of your current, subtract your phase angle of your voltage source or your voltage. All right. And this is a minus. And if this value right here that you get is a negative value, then it's lagging. If it's positive, then it's leading. Okay. And so in this case right here, this is a negative value. So that means it's lagging. And so therefore the power factor is 0.95 lagging, which means that the current is lagging the voltage source by 18.97 degrees. All right. Another way you could have determined whether or not if it's lagging or leading is look at your impedance. All right. So if your impedance has a positive angle, then it's always going to be lagging. It's always going to be a lagging power factor. If it has a negative angle, then it's going to be a leading power factor. All right. I know that can be kind of confusing, but if you have any questions, feel free to reach out to me. Let me know what question that you have on this one. All right, so let's move on to the next example. Example 2 is going to be a parallel. Oh, let's go back up this one. All right, so another way you can determine whether or not if the power factor is lagging or leading is look at your reactance, right? Your capacitive and inductive reactance. If you have more capacitive reactance than you do inductive reactance, then you're going to have a leading power factor, and vice versa. If you have more inductive reactance than you do capacitive reactance, then you're going to have a lagging power factor. So let's look at these two right here in relationship to what I just said. So right here we can determine that we have your capacitive reactance is 17.68 and your inductive reactance is 34.87. So therefore you have more inductive reactance than you do capacitive reactance. So therefore that statement holds true that this power factor is going to be lagging. All right, so let's go ahead and move on to example 2. So example 2 says calculate the total impedance, total current through each branch using a current divider and the power factor. All right, so first step that you want to do, just like what we did before, is convert everything to its respective reactance. In this case, we only have an inductor. We don't have a capacitor this time. And so we want to do that accordingly. So XL1 equals 2 pi FL1. And so once you calculate that all out, you get 50.27 at an angle of 90 degrees. All right, so now here, I want to combine these two together so I can add this in parallel with R1. So that's what I'm going to do here, and I'm going to call it Z1. So Z1 equals R2 plus XL1. And so you get 25 ohms, which comes right here, plus 50.27 with an angle of 90 degrees, which comes from your inductive reactance. And once you calculate that out, you get 56.14 with an angle of 63.56 ohms. And so now we're at a point where we can add these two impedances in parallel. So pretty much the equivalent circuit that we're working with look something like this over here. So you have your R1 that's in parallel with Z1. So we just added these two together, combined is equal to your Z1, which is that 56.14 at a phase angle of 63.56. All right, so to add them in parallel, this should be very familiar from what you have learned through circuits 1. So you get your 1 over and the whole 1 over method. So 1 over R1 plus 1 over Z1. You plug and chug, and you get 31.09 with an angle of 29.73 ohms. So that's your Z total, right? Okay. So right now, you should be able to determine whether or not if this power factor is leading or lagging. Take a second to think about it based off what we talked about before. Okay. All right. So to calculate your total current, you get your voltage source, which is V1 divided by Z total, which you get 3.22 at an angle of negative 14.73. And so here's your current divider formula right here. So IR1, which you're trying to find the current through this R1 branch right here. IR1. Okay. So you take your total current, multiply it times your total impedance, divided by your element of choice or impedance of choice. So in this case, we wanted to do it for the branch that has R1 in it. And so once you plug those values into your calculator, you get 2 at an angle of 15 degrees amps. And do the same thing for your Z1. So remember, we found Z1 to be 56.14. So remember, we found Z1 to be 56.14 at an angle of 63.56. All right, so once we plug that into our calculator, we get 1.78 at an angle of negative 48.56 degrees amps. All right, so now to double check your work, remember that Kirchhoff current law means that the current into the current in equals the current out. So you got your I total coming into this junction right here. And then you have this IR1 and IZ1 leaving. And so if you add your IR1 and your IZ1 together, you should get what we calculated for I total. And so why don't you go ahead and take a few seconds to try to plug that into your calculator and make sure that is still true. All right. All right, so we're going to use the same methodology that we used before to determine the power factor and whether or not if it's lagging or leading. All right, so power factor, you can use your phase angle from your total impedance, which is your 29.73 degrees. All right, and so we get 0.87. So at this point, we don't know if it's lagging or leading. All right, or we can use the theta V, your voltage source angle, minus your voltage of your current source. And so we get the same thing. So 0.87. So lagging or leading, so you take your current angle, subtract it from your voltage angle. And if it's negative, it's a lagging power factor. If it's positive, it's a leading power factor. So in this case right here, we get a negative number, which is negative 29.73, which is a lagging power factor. So that means the current lags the voltage by 29.73 degrees. And so which makes sense, because when you come up here, come up here back up to your Z total. Remember how I told you that if it's positive, it's going to be a lagging power factor no matter what. If your total impedance has a positive angle, it's going to be a lagging power factor no matter what. Always. All right. And likewise, by inspection, if you just only look at the circuit, you can tell it's lagging. This is how, because you don't have any capacitors in here. You don't have any capacitive reactance. So the only thing you have is a resistor and inductor. So remember what I said before, if your total impedance has more inductive reactance than capacitive reactance, then it's a lagging power factor. All right, and this one only has inductive reactance from this inductor right here. It doesn't have any capacitor here. So, but if this circuit right here did have something like this, where it had a capacitor right here, then you can't really do it by inspection. You have to calculate the total impedance in order to make that determination. But because this one only has just an inductor and resistors in it, but really because it only has an inductor in it, by inspection, you can say that the power factor is lagging. Likewise, if this inductor wasn't here and it was a capacitor here, then you can already say that the power factor of this network right here is going to be leading. You don't even have to do any work. You can just determine by inspection that it's going to be a leading power factor. All right. And so that's it for this example. So hopefully these two examples right here should help you out with the homework. If you still have any questions or any confusion, like I said, this power factor right here, it is kind of a beast to try to understand or try to wrap your head around, what's going on. But if you need me to provide a better explanation, or need me to meet with you, just feel free to just reach out to me. But with that being said, that's going to conclude this video, and thank you for your attention.